You learned how to count when you were very young, and consequently the idea of counting seems like a very simple thing to you. But the idea of our counting system, what we call the base 10 counting system, was a brilliant innovation invented by an ancient Arab mathematician. The ancient Greeks, for example, never came up with it, and when it spread to Europe, it revolutionized the way we were able to do mathematics. One wonders what Pythagoras and his team would have thought of a little picture like this that illustrates the base 10 counting system. We have a succession of wheels, and each wheel has 10 symbols on it, the digits 0 through 9. And each wheel turns up successively through the digits, and when a wheel gets to 9, it rolls back over to 0 and simultaneously causes the wheel just to its left to move one position. Every wheel obeys that one simple rule, and that's all there is to the counting system. But what makes the counting system really powerful is that the digits on each wheel represent a number of groups. The second wheel advances only after every 10 clicks of the first wheel. That means the number on the second wheel counts the number of tens, and when the first two wheels both get up to 9, so that we have 9 tens and 9 ones, we roll over and the third wheel counts up and it's counting the number of 100s. And 100 is 10 times 10. It's 10 squared. Now, the fourth wheel, it's going to turn out, counts the number of 10 cubes. And that might seem like a coincidence. You might ask yourself, why would it be true that after 999, which is 9 times 10 squared, plus 9 times 10 to the 1, plus 9 times 10 to the 0, why is it that right after that, when you add 1 to that number to get the next wheel to turn, you end up with exactly 10 to the third? And one way of seeing why that's true is by grouping the 10 to the 0s. You get 9 of them and 1 of them is 10 of them, so you have 10 to the 1. And then you group the 10 to the 1s, and you get 10 to the 2, and then you group the 10 to the 2s, and you get 10 to the 3. And if you see that's true, you should see that would be true even if we counted with a base 7 system instead of a base 10 system. If we added up, instead of 9 times 10 squared and 9 times 10 to the 1 and so on, we added up 6 times 7 squared and 6 times 7 to the 1 and 6 times 7 to the 0, and then we add one more to that, do we get 7 to the third? And if you actually do the arithmetic and you add up those values and then you add one more to them, you get 343, and you can ask your calculator to confirm for you, yes, that's 7 to the third. Another way of seeing why that has to be true is by looking at this picture of what I'll call base 7 blocks. We have unit blocks, and then we have blocks that are worth 7 units, and we have blocks that are worth 7 squared units, or 49 units. And if I want to build a cube that's 7 by 7 by 7, then I would start laying down the 7 squared blocks. 1, 2, 3, 4, 5, 6. Darn, I'm one short. I only have 6, but I needed 7. I only have a 7 by 7 by 6 figure right now. I wanted a 7 by 7 by 7. So I'll start using my other blocks to fill in the top layer, and I'll put down 7 of these. 1, 2, 3, 4, 5, 6. Darn, I'm one short again. I still have a space I need to fill in, so I'll fill it in with units. I need 7 units more. I put in 1, 2, 3, 4, 5, 6. And once again, I'm one short. And so you see that 6 times 7 squared plus 6 times 7 plus 6 times 1 is 1 short of 7 to the third power. And if you understand this picture, then you should see that the base 10 counting system doesn't have to be base 10. It would work just as well if it were base 7 or any base. Algebraically, this is a consequence of a factoring fact that b cubed minus 1 can be factored into b minus 1 times 1 plus b squared. So in the case with b equals 7, for example, we have this fact. If I distribute the 6, then I get the result that I was just showing you graphically. And this shows that for any base b, the fourth digit represents the number of b cubed. And this can be generalized even further if you remember how to sum a geometric series. So that shows that, for example, the 5th digit is going to represent the number of b to the 6ths, and the 8th digit is going to represent the number of b to the 9ths, and so on. So we don't have to count in base 10. We could count, for example, in base 5. Here's a picture of base 5 counting wheels. Each wheel has 5 symbols on it, the digits 0 through 4. And the rule is that when the wheel gets up to 4, it rolls back over to 0 and takes the next wheel one turn with it. It's the same exact rule we used for the base 10 counting system. Now let's back up again and see what the correspondence is between counting in base 5 and counting in base 10. And you can see that we've gotten up to 311 in base 5, and we've only gotten up to 81 in base 10. And we'd write that this way: 311 base 5 is equal to 81 base 10. What that means is that 3 times 5 to the 2 plus 1 times 5 to the 1 plus 1 times 5 to the 0 is equal to 8 times 10 to the 1 plus 1 times 10 to the 0. 3 times 25 is 75, plus 5 is 80, plus 1 is 81. So what if we had learned how to count in base 5 instead of learning how to count in base 10? Could we do all the same arithmetic that we did in base 10? For example, we know that 81 is 9 squared. How would I write the same fact in base 5? 311 in base 5 is the square of, how would I express 9 in base 5? 9 is 1 5 plus 4 ones. So 14 in base 5 represents 9. So in base 5, 311 is equal to 14 squared. Now I can check that fact by doing multi-digit arithmetic on 14 times 14. And I'm always going to put the little subscript 5 to show that I'm writing numbers in base 5. I start out with 4 times 4, and 4 times 4 is 16. 16 is 15 plus 1, which is 3 5s and 1 1. That's 31 in base 5. 4 base 5 times 4 base 5 is 31 base 5. So I put the 1 down, I carry the 3, so I put the 3 up here, and next I'm multiplying 4 times 1, and I'm adding 3. So 4 plus 3 is 7, which is 5 plus 2, that's 1 5 and 2 1s, so 4 plus 3 in base 5 is 12. And now I put down the 12, and I've got my first result to sum. 121 in base 5 is 4 in base 5 times 14 in base 5. And then I go to the next digit. 1 times 4 is 4, and 1 times 1 is 1. That's easy enough. And I get the next row, which is 14 in base 5. Now I add them up. 1 plus 0 is 1. 2 plus 4, that's in base 5, that would be 11. 1 5 and 1 1. So I put the 1 down, I carry the 1, and the last column is 1 plus 1 plus 1 is 3. And I get the correct result, 311 base 5. So I can completely do arithmetic in base 5. There's nothing special about the number 10. And now I'd like you to pause the video and try something for me. I want you to do the same trick and write the multiplication problem 9 times 9 equals 81, but translate it, instead of base 5, translate it into base 3. And pause the video. I think this will give you some good insight. And when you're finished, start playing the video again. When I was a kid, in the year 1976, we celebrated our nation's bicentennial, which was an important year because it was bi, meaning 2, it was 200 years from the date our nation was founded, and 200 seemed like an important number, but that was only because we count in base 10. If instead we counted in base 9, then you would all right now be looking forward in anticipation 5 years from now when we celebrate our nation's tricentennial. 300 years in base 9 from the founding of our nation. And by the way, if you're wondering what year it is right now when I'm making this video, it is the year 2677 in base 9. So there's nothing special about the number 10. And this brilliant ancient Arab mathematician that came up with the base 10 counting system just chose it arbitrarily. We don't know why the number 10 seemed like such an important number to the Arab mathematicians. We can guess that maybe it had something to do with human anatomy. Now this will take some getting used to. I know that you're conditioned to think that the base 10 counting system is going to be easier to use because, for example, you can divide by 10 very easily. But in any other base, there's a corresponding easy operation. In base 7, for example, if you wanted to do the arithmetic problem, 63 divided by 7 equals 9. In base 7, here's what it would look like. That's 63 divided by 7, and dividing by 7 is easy. You just strip off the 0, and you get the number 9 in base 7. In fact, if you want to go one step further and take the number 12 in base 7 and divide by 7, then you get 1.2 in base 7. And that just means that 9 divided by 7 is 1 2/7, because you see this number 2 here, the first number to the right of the decimal point, is the number of sevenths. That's the sevenths place. So we have 9 divided by 7 is 1 2/7. By the way, I called this a decimal point. Strictly speaking, it's not really a decimal point because decimal contains the prefix DEC, which means 10. And really it's only a decimal point when we're in the base 10 counting system, which is called the decimal counting system. Now there are 4 bases that I know of that have their own names. They are decimal, binary, octal, and hexadecimal. Base 10, base 2, base 8, and base 16 respectively. Decimal is the base that we normally count in, uses the digits 0 through 9. Binary is the most extreme case. It only uses the digits 0 and 1. Here's what it looks like to count in binary. You can see that you can get up to numbers with many, many digits very quickly. That's because the second digit is the 2's place, the next one is the 4's place, the next one is the 8's place, the next one is the 16th's place, and so on. Binary is very important because computers store all their numbers in binary. Computers store numbers by setting voltages on pins. Each voltage is recorded either as being on or off, and that represents a 0 or a 1. Each pin is called a bit, and a string of pins in succession that represent the digits of a number expressed in binary is called a byte. So it's important to become familiar with binary counting. The next base, octal. Octal uses the digits 0 through 7. And then hexadecimal uses the digits, well, we don't have enough digits in the Arabic counting system, so we have to throw in some letters of the alphabet, and we go up through 9, and then we count A, B, C, D, E, F. Octal and hexadecimal are very important because of their relationship to binary. And you probably have a sense of that relationship if you paused the video before, as I asked you to, and computed 9 times 9 equals 81 expressed in base 3. Did you really do that? Now I'm going to explore the relationship between binary, octal, and hexadecimal by doing a calculation of 1/13 in octal. To do that, I'll write 13 in octal, which is 1/5, and I'll divide it into 1.0000 using long division. I'm going to go a little fast, so you might not be able to follow along. You should get a piece of paper and try it yourself. The more familiar you are with long division, the easier this will be to follow. First I asked myself, how many 1/5s go into 1 0? And the answer is 0, so I put a 0 in the quotient. Next I asked myself, how many 1/5s go into 1 0 0? And that's not such an easy question. I really need to count by 13s. So I'm going to write down a list of the multiples of 13. 13, 26, 39, 52, 65, 78, 91, and the last one I need to write down, 104, is 8 times 13. You can see that expressed in octal, it's just 13 with another 0 added on to the end of it. So I really only need the first 7 multiples of 13. And then I look for the largest multiple that's smaller than 100, 4 times 13. The next digit in the quotient is a 4, and I write down the product of 4 and 13, and I subtract using base 8 subtraction, and then I bring down a 0. I use my table to see that the next digit is going to be 7, so I write a 7 and a 133, and I subtract using base 8 subtraction. I bring down a 0, and then I see my next digit is going to be a 3, and I write down the 3. I bring down the 4, 7, I subtract, and I get a 1. Bring down another 0, and I see my next digit will be 0. I bring down another 0, and I start to recognize that the whole process is going to repeat, which means I have an infinite repeating decimal for my answer, 0.0473 repeating, and I have figured out that 1/13 expressed in octal is 0.04730473, and so on and on forever. Now that I've done the long division work to compute this number expressed in octal, I want to show you how easy it is to translate it to binary, and then how easy it would be to translate that to hexadecimal. So I'm going to take each digit and I'm going to express it as a 3-digit binary number. 0, for example, would be 000. Now the next digit, 4, expressed in binary, would be 100. The next digit, 7, is 111, 3 is 011, and then we have 0 again, and we end up with an infinite repeating decimal whose repetend is 12 digits long. It's 0.00100111011 repeating. Now that I've expressed 1/13 in binary, it's very easy to express it in hexadecimal. Instead of grouping the digits by 3s, I'm going to group them by 4s, so that I take 0001, what I've circled over here, and I write that as a single hexadecimal digit. Then I take 0011, which is 3, 1011, remember that this is a 1 plus a 2 plus an 8, that's 11, and 11 is B in hexadecimal, so I write a B. And then I see that I get a repeating infinite decimal again, and I've got 1/13 expressed in hexadecimal as 0.13b. That's the reason octal and hexadecimal are so important. It's because it's very easy to translate from binary to either one of them. Now I'll show you a little secret code game that'll give you some practice with this. We're going to decode a secret message. First I'll show you how the message is encoded. We take the letters of the alphabet. There are 26 letters of the alphabet, and each one of them is expressed as a 5-digit binary number. So A is 1, B is 2, C is 3, D is 4, and so on, all the way down to Z, which is 26. 26 would be 16 plus 8 plus 2. With these substitutions, we could take a simple word like spleen and rewrite it as a string of zeros and ones. The S is 19, so that becomes 10011, 16 plus 2 plus 1. The P is 16, so that's 10000. L is 12, which is 8 plus 4, so that's 01100. E is 5, which is 4 plus 1, so that's 00101. Another E is another 00101. And N is 14, which is 8 plus 4 plus 2. That's 01110. The next step is to take this string of ones and zeros and group them in groups of 4 so that I could write a hexadecimal number. I do have to tack on 2 zeros at the end because I didn't have a multiple of 4. And then I take each group and compute its numerical value. This is 8 plus 1 is 9. This would be 8 plus 4 is 12. This is 1. This is 8. This is 4 plus 1 is 5. This is 2. This is 8 plus 2 plus 1 is 11. And this is an 8. And then I write them as single hexadecimal digits, and I get 9C1852B8. And that is my secret code meaning spleen. Right? If you were able to follow those directions on how I encoded the word spleen, then you should be able to decode a word. And I'm now going to give you the decoding puzzle. I want you to identify the person who is responsible for the following quotation. By trying, we can easily learn to endure adversity. Another man's, I mean. Name the author of this quotation, and the secret code for this author's name is 6864B052E14B8. Good luck!